Building software is hard, and it's hard because it's complex. If you're like me, then Scala wasn't your first language, so you came with some baggage. Now, in many cases, that baggage is a good thing because it makes it easier and faster to pick things up. We stand upon the shoulders of giants, even when those giants are earlier versions of ourselves. But at the same time, it can also hinder you because you tend to fall back on that knowledge in order to be productive. Object-oriented programming and functional programming are very different paradigms, and the beauty and bane of Scala is that it lets you play with both. To illustrate the difference in approach, let's look at a mechanical watch. OOP's answer to complexity is to encapsulate the complexity inside objects. All of the gears are hidden away, so you don't have to worry about them when you use the watch. You use the API instead. The object is king. Functional programming mainly tries to reduce complexity. Immutability, referential transparency are all means to simplification. But it too, like OOP, encapsulates. It just does so through the function. The function is king. Both approaches then compose larger, more complex software from their respective building blocks, the object and the function. About a year ago, my team evaluated a number of different HTTP frameworks to replace our aging Scalatra stack. The winner of that competition was HTTP 4S, quite a clean, minimal, functional framework. The predominant style we were using in the older stack was one with functional in the small, OOP in the large. That is, we were writing functional code, what I like to call filter map magic, but the microservices were being hung together in an OO way, using an object-based approach and making use of inheritance and classic object-based dependency injection for testing. More recently, we've been looking at a more functional way of hanging these things together. To start with, we'll go right to the beginning and look at what a function is and what functional composition are. Then we'll look at composing functions using the standard library in more depth before pressing on to composing with higher-kinded types. Basics, standard lib, higher-kinded types. Part 1, the basics. So I'd like to take you back in time to when you first encountered Scala. And if your experience was anything like mine, then you probably encountered a def like this. Even if the syntax is a little different, it's fairly easy to recognize the argument, return type, and implementation. I'd say it's quite familiar whether you come from Java, JavaScript, C# or Python. In fact, it's very similar to Python. It uses a def keyword and everything. So it looks like a function. It walks and talks like a function. And in fact, if we were using Python, it would be a function. But in Scala, we're a little bit more strict with our typing. The problem with this is that despite how accessible it is when you come to Scala, it isn't actually a function. It's a method. So if what we've just seen is not a function, but a method, then what is a function? What is a method? And what's the difference? Let's illustrate this with an example. So here we have backwards, which is a method that returns a string. We know this because the return type is a string. Hail the static typing. Get backwards is a method that takes no arguments and returns a function of string to string. That is, the return type is a function with the same signature as backwards. It takes a string and returns a string. Now you can use these in the same way. Applying them with an argument yields a result that you can print or do whatever you want with. But when we try to assign the functions to variables, get backwards works, but backwards does not. Now, we can actually take the function from a method and store it in a val, but we need to give the compiler a little bit more explicit information to do so. As seen, just assigning it to a val won't work, because there's a little bit more work that needs to be done in order to be able to pass a function around as a variable. Applying using an underscore or explicitly stating the type of the val is enough to trigger this. But the key takeaway here is that it shows us that there's a difference between a method and a function. They are not the same thing. We can store the function as a val, and unlike the def, this is a function. In fact, every time you see that arrow operator, you know it's syntactic sugar for a function. Previously, we saw that a def could create a function and be coerced to return a function, but in this case we are directly assigning it. There is an important distinction. A val is eagerly evaluated. That is, the value on the right-hand side is evaluated and assigned when the val is declared. However, this occurs once. A def is evaluated every time it's called. A lazy val is like a regular val, but it isn't evaluated when it's declared, it's evaluated when first called or used. So if we don't call it, it never gets evaluated. If we call or use it 3 times, then the right-hand side is evaluated once on the first call. So now we know that a def is evaluated every time you call it, just like a function. A val is evaluated once when declared, and a lazy val is evaluated once the first time it's used. Let's look at what a function is. A function, as we pass it around in Scala, is an object. So you can think of a function as being an instance of a particular trait that exists on the heap in memory. When we assign a function to a val, we store the memory location of the function object in the val. When we apply a function, we call the object's apply method with the arguments. Here, we are explicitly creating a function1 object, which takes 2 type parameters. The first is the input, and the second the output of the function. In fact, string to string is syntactic sugar for this object. This is important when you're thinking about how a def is evaluated on every call. If you return a function from a def, you are creating a new function object every time it's called. The function 1 defines a function with 1 input parameter, but it's not the only function trait. There are as many function traits as there are tuples, 23 of them, from 0 to 22. A function 0, as seen here, is a 0 argument function, the same as empty brackets to something. We've seen the syntactic sugar describing function signatures now. Here, we have 2 functions with references stored in vals, double and inc. These have been implemented using the abbreviated syntax, which is the same as a to a star 2 and number to number plus 1. Composition is a means to take multiple functions like these and put them together to produce a combined effect. We can achieve this most easily by chaining application of the functions. Here, we apply double with the input 5, and then we take the output of that function call and feed it into the second function as an argument. This can also be achieved by inlining the function calls rather than storing the intermediate result in a val. However, it would be even more useful to be able to compose functions without applying them. That way we could reuse blocks of logic by composing them from other functions, whether those other functions are simple single functions or composed blocks themselves. If we wanted to produce something reusable rather than eagerly composing on the fly, we could create a new function. This delays the execution of the composed functions until we apply this function and pass in the input argument. Then it feeds into the first and executes down the chain until it returns the output from the tail. However, the syntax here doesn't scale very well, and it becomes harder to read as you increase the depth of nesting. Plus, you have the added difficulty of attempting to read the chain from right to left. Let's take a look at what other options there are. Part 2. Composing with the standard library. So we have the compose function. And what this does is allow you to provide another function as an argument to your current function, and it will compose the two functions into a new function, just like we did manually, where the other function is applied, followed by the current function. Now this operates just like the dot compose notation in maths, where a dot b produces a function where the argument is first applied to b, and then the output of that is applied into a. Or in this case, whatever is passed in is doubled before being incremented. So we've improved the readability somewhat using the compose method by avoiding the nested calls. We can use whitespace, just like in Python, to make it a little easier still. But we're still stuck with this problem where we have to read from right to left. Now if that's easier for you, then compose is your function and you can stop there. If it's not, however, there is another method provided to us that we can use instead. And it's called and then. It works exactly the same as compose, only the order of composition is reversed. So if we use it to compose inc and double, it will apply inc first, followed by double, which has the effect of switching the reading order of the compose functions from right to left to left to right. Now, I personally prefer this style. I find it easier to read and reason about. But as we've seen, you have the choice, so use whatever works best for you. Now, we've seen this already, but I just wanted to be explicit and clear that in order to compose functions, the signatures must match. If your output from one function is a string, then the next function in the chain must take a string as its input. Here we have a config to db result, a db result to big int, a big int to big int, and then a big int to JSON. Now because each signature in the chain matches up, as in the output of A, db result matches the input to B, db result, etc., then we can produce a composed function of A and then B and then C and then D. But we couldn't do an A, compose B, compose C, compose D, because that's the same as D and then C and then B and then A. Before we wrap up this section, I'd like to highlight a few gotchas. Result here is perfectly fine. Unit num is a function of unit to int, and double is an int to int. The signatures line up and we can compose them. However, if we have later num and we try to substitute it for unit num, it won't work. This is because empty brackets are treated as no arguments, which means that later num is not a function 1 of unit int, but a function 0 of int. And of all 23 functions, only function 1 has the methods compose and then defined on it. Part 3. Higher kinded types. Now, of course, when you see a picture like this, you know we're going to talk about monads. Don't worry, we open the lid, cat's fine. If you're unfamiliar with monads, for the purpose of our functional composition, you can think of them as a context or a box which wraps a value or a type. Kind of like how a variable is a box with a value in it, so that if you had val x, you'd have a box with x written on the front, equals 5, the value 5 placed inside the box. A monad is a different kind of box that you set up that takes a type, which is a fancy way of saying it's generic. You have to provide the wrap type, the cat in this example, to construct your new monad. The box itself provides context. A list is a monad. If it's a list of cats, then that's a very different meaning to an option of cat. The list means that there is a sequence of cats. The option is all about whether or not the cat exists, a softer version of Schrodinger's cat. But you can have a monad with more than one type. perhaps the box has a cat and a dog in it. Or with types that wrap other types. So you can have a cat in a box, just like HP or Amazon used to do, where you'd receive a delivery and then open a sequence of boxes before reaching the item. In this case, you can think of the boxed cat as a turtle. In fact, it's turtles all the way down until you hit elephants. An important takeaway for functional composition are a couple of methods on your context or box, map and flatMap. If you want to pet the cat, you need a way to play with the thing inside the box. A functor has a map method which allows you to provide a function to be applied to the contents of the box. A monad has this, but also has a flatten method which allows you to unbox cats or turn turtles back into cats. A good example of this is if you had a list of string and passed a function in via map which took each string and split it into a list of chars. You now have a list of char. We're back to turtles. Flatten takes a box of thing and returns a box of thing. It flattens the structure. The flatMap method therefore combines map and flatten such that you take what's in the box, apply a transformation that results in a box of thing, which is then flattened to return a box of thing back. Quite commonly, you'll have functions inside a context, such as a future, task, or an I/O, and this presents a problem. As we've already seen, in order to compose, our output from one function must form the input to the next. When we start calling functions that wrap results inside a future, say, we have to make a decision. We could simply write our functions to take a future boolean or an I/O boolean as the input, but this might result in a set of small building blocks which are less composable or interchangeable with other components. You may also feel that it pollutes the signature. So here, we're using flatMap to reach inside the I/O context and get a handle on the contents before applying a transformation to it which returns another I/O. And we've done this in a chain. It's very similar to the first way we approach composition. We're nesting our calls, we're delaying evaluation using the function we've created to wrap the composition. We just have the additional need to nest the flatmaps here as well. All in all, it works, but it's not particularly easy to read. Let's go one better using a feature of the standard library. This is basically syntactic sugar for the hand-cranked flatMap we've just seen, and it's probably the most common form of handling this sort of monadic chain that you'll see. I think that's because it's a lot more readable whilst doing the job. The opening line in the for comp sets the context of the comprehension, so in this case the context is an I/O. The result, when yielded, will be wrapped in that. So even though we have a handle on result as a boolean inside of here, we're inside that I/O context, and so the return value will be an I/O of boolean. It's cleaner, but we're still reliant on wrapping this eager composition inside a function call in order to delay it. It would be nice if we could achieve what we did with the standard libraries compose and then, wouldn't it? And so we meet the Kleisli. The Kleisli allows us to compose functions while ignoring the context on the outputs. You can think of this as being like a monad transformer for functions. If we have a function with a signature of int to I/O of string, then when we lift that into the context of a Kleisli, again, another monad, turtles all the way down, we get a signature of Kleisli I/O int string. That is, the context is the first type parameter, the input the second, and the extracted return type the third. To lift a function into the context of a Kleisli, you simply call the apply method on the Kleisli. Now, as we've already seen, you can do this explicitly, Kleisli.apply, or you can use the more usual syntax where you just call Kleisli, use the apply brackets. Now we're back to when we use the standard library for combining functions using methods defined on the function1 trait. Only now we're doing so while the outputs are wrapped inside of whatever context we're using. There is still a little syntactic sugar to make this even more convenient though. So previously we lifted all of our functions into Kleisli in order to compose them, but the Kleisli itself provides the ability to perform both the lift and combination in a single step. You still need to lift the first function to get access to the methods, but after that you can either use and then k or compose k if you're using Scala Z, or Cats simply overloads the and then operator, so there's no change between providing a function or a Kleisli wrapped function in the chain. Being a wizard is great. You get to wear cool clothes, wave a staff about, and read arcane symbols. Scala Z has some arcane symbols. Here we have the little fish, and this operator is a drop-in replacement for the combination methods we've seen. The fish swims in the direction that you'd read the combination, so this is an and then. If the fish pointed or swam to the left, it would be the same as compose. Below, we have a bigger fish. This is the and then k or compose k, and the direction tells us which of those it is. Now, some people like these sort of symbols. I have a soft spot for them. But at the same time, you need to recognize that trying to Google something like this can be a little tricky, and there's not much help as to what they do from the naming. You kind of have to know what it does or is first. If you use Cats, then there's no choice to be made because it doesn't have these symbols. So now we've seen the big fish, the little fish, and the cardboard box. It's time to retrieve our function back from the Kleisli. .run. That's it. So if you want to retrieve the function back, calling the run method will return you your extracted function. And at the same time, you don't necessarily need to do it because the apply method on your constructed Kleisli will pass through the arguments you provided into the encapsulated function. So you don't need to extract the function out to run it, but if you needed to pull it out to pass it into something that's requiring a different signature, then .run is how you do it. Readability. As you can see, an advantage of functional composition is this ability to go from a very small, concise piece of code to a much larger, very verbose piece. Now, the top shows a couple of objects being passed into a method, which has responsibility for constructing the handler. Traditionally, a lot of the functionality shown in the second example occurs within the createHandler method and may or may not be hidden away behind access modifiers. What I like about the compose version is the story that it tells. Now, you can kind of do this in the OO model if you follow clean coding practices, but I feel that in practice this doesn't quite tell the story as cleanly. It tends to be eager, with nested calls and method application that get in the way of reading what's going on in the way that we've already seen earlier. Plus, by default, it tends to be encapsulated within the classes. Also, if you're not happy with the block of code constructing the handler in the composition example, you can always go ahead and encapsulate that inside of another function and go and hide it somewhere. Reusability. Another thing I like about having the construction exposed is that it acts as a constant reminder that you have these blocks or chunks available for use. The highlighted sections show how, through the organization of these functions, that a different kind of handler may be able to reuse some of these components, perhaps replacing the transcoded handler parts or just the calculate timecode data function. Of course, reusability is a key part of all software design. The dry principle is well known, but perhaps this method provides a clearer description of the program as it's composed. One thing you might notice with a more functional approach is the distinction between the description of the program and the execution of it, a line perhaps somewhat more blurred in other approaches. Robustness. Now, I had to massage this a little to get a word starting with R, but this is one of the best things I've found with functional composition. I love the testing. mainly because I dislike working with Makito, deep mocking, and generally having these huge object dependencies thrown around, to the point where I view it as a code smell. Now, I know that many people really like Makito, and it's a fantastic library, and when you need to mock a huge Java class, then it's much, much better than the alternative. But imagine a world where you didn't need to do that. And that's the world that I like to pretend I live in. And this is what you get. You want to stub a list of files for a function? Go ahead, ignore the input, return whatever you need. How about testing failure response? No problem, just blow it up. And for those times when you need to verify interaction with a function, you can use a promise or a ref to grab whatever the function was called with. Right, downsides. I gave 3 benefits, so I feel it's only fair to point out 2 downsides. Firstly, there is a time investment. Everything unknown requires that investment to learn, so there's a cost involved. You need to consider if it raises the barrier to entry, and I guess this is down to the individual team to find what works for you. Despite what you might think coming to a conference like this, the vast majority of Scala developers do not appear to be writing highly functional code in Scala. Not everyone is able to use the cool functional libraries and tools that you may hear about. There's a lot of Java in production, and a lot of functional in the small. Map, filter, magic. It's hard enough hiring Scala developers. How easy is it hiring Scala developers that have or can learn these skills? Do the benefits gained from keeping developers stimulated, growing, and happy outweigh the cost? Another downside is that it changes the way in which you tend to navigate a little. With an OO approach, jumping to the definition of an injected class is super fast in your favorite IDE. With function signatures, you may end up popping over to usages to see the source of the function instead. Your mileage may vary. We all float down here. Come join us. So I'd like to say thank you to Pixabay for some of the pictures that you've seen, a couple of those, and also to Unsplash, from which I've pilfered a larger number of the images. This presentation will be up on the ScalaX website. There's the link. I don't know how quickly it's going to happen for this one because the conference is huge in comparison, but I noticed with P3X the talks were going up the same day as the talks were done, so maybe this year will be up really, really fast, but certainly soon. If you are interested or have been interested by what we covered in the talk today, there is the tutorial video on YouTube, which this talk is based off of. So you can have a look there. That's a code along, so you'll see live coding taking place. There is also a pre-recorded version of this talk with the slides that's also available on YouTube, or will be when I switch it to public. So you have a variety of different options for watching this material if you are interested in that. Slides, because everyone asks about slides, as if all the other material isn't enough. But I guess if you do want to sort of read through the bits, I have put them available. They're up on GitHub. That's the link. And if you would like to follow me, feel free. I love collecting friends, followers, etc. on Twitter and also on LinkedIn. Just looking at the time. Thank you.